This is Geology Bites with Oliver Strimpel. In several previous episodes of Geology Bites, such as the ones with Sarah Russell and Harold Connolly, I've talked to researchers seeking to understand the early history of the solar system through studies of asteroids. Asteroids are especially valuable in this regard because they preserve a record of the early solar system. There are many unanswered questions about the early history of the solar system. In particular, did the giant planets form roughly at the distance from the Sun they presently occupy, or, as some theories predict, have they migrated to their present positions after they formed? The discovery of other solar systems with radically different configurations of planets has made this question more pressing, since it appears that the configuration of the solar system is highly atypical. It turns out that certain asteroids called the Trojans that are locked into the same orbit as Jupiter offer us the best opportunity to discriminate between the various models of solar system evolution. And that is why a spacecraft called Lucy is now well on its way to a rendezvous with these asteroids. Hal Levison is principal investigator of the Lucy mission. He studies the dynamics of astronomical objects and in particular the formation and long-term behavior of solar system bodies. He is one of the original proponents of the NICE model, a scenario that proposes the migration of the giant planets from an initial compact configuration closer to the Sun to their present positions. He is chief scientist in the Department of Space Sciences at the Southwest Research Institute in Boulder, Colorado. Hal Levison, welcome to Geology Bites.
Thanks for inviting me. It's a pleasure to be here.
Can you explain how it is that the small bodies in the solar system have survived as fossils of the very early solar system?
Let's take a step back. Our understanding of how planets form is that originally the solar system consisted of gas and a bunch of dust, and the dust slowly built up over time to make first pebbles, then rocks, then mountains, then asteroid-sized things, all the way up to the planets. So the planets are made of these things, but planet formation is not 100% efficient. And as a result, we have a population of small bodies that are basically leftovers, the dregs of planet formation. And that's what asteroids and comets are. And the reason why they're interesting for somebody like me who's interested in how the solar system formed is that while planets have done their own thing, they have internal geology or they have weather that have changed what the planets look like, these small bodies are basically fossilized at the time that the planets formed. And so if you really want to understand how the planets formed, these are the best places to go, I think.
Okay, so the Trojans are asteroids, but they're not in the asteroid belt that lies between Mars and Jupiter, but further out, and actually in the same orbit as Jupiter, with one group of Trojans leading Jupiter in its orbit by about 60 degrees, and the other trailing Jupiter by the same amount. How come they're herded into that space, and how do they compare to the asteroid belt in terms of their numbers and the volume they occupy?
So Trojans are in the special balance points gravitationally. And the way to think about it, although it's technically not really right, is that if you put an object in front of a planet by 60 degrees in its orbit, the gravitational attraction of the planet and the Sun, plus the centrifugal force of the orbit, balances out in such a way that the object put there stays there forever. And that's how come we know these objects are actually very ancient objects. And what makes them interesting from a solar system formation point of view is they're left over from the outer planets. While we think most asteroids in the asteroid belt are leftovers from the rocky terrestrial planets, these guys come from the outer solar system, and that's what makes them interesting. Now, the population is comparable, somewhat less, but comparable to what is in the main asteroid belt today. And they occupy actually a really small region of orbital element space They're actually more concentrated in a way than the main asteroid belt is.
I said in the introduction that the Trojans offer us the best opportunity to distinguish the various models of solar system evolution, and in particular to test the NEAS model. You were one of the original proponents of that model. What motivated the development of this model, and can you explain how the solar system evolved according to the model?
Sure. What motivated me to work on the model, and there's a lot of reasons why people started questioning whether the planets that we see in the outer solar system today formed where we see them. So there's a lot going on there. But the thing that motivated me is the realization that Uranus and Neptune, which are the ice giants in the outer parts of the solar system, could not have formed where we see them today after Jupiter and Saturn formed. So the classical thinking of planet formation is that the planets in the outer part of the solar system form more slowly because the orbital periods are longer. So things just take a lot longer to get going out there. And we realized that that's not true. Uranus and Neptune can't have formed after Jupiter, Saturn formed. So we looked at a way to allow the four giant planets to form at the same time. And that led us to the idea that the solar system formed in a much more compact configuration, and that some dynamical event moved the planets around to where we see them today. So the NEAS model basically hypothesizes that all the four giant planets formed in a much more compact configuration, let's say within 12, 13, 14 astronomical units from the sun. So an astronomical unit is the average distance between the Earth and the sun. Currently, Neptune, which is the outermost planet, is at 30 astronomical units. So we're hypothesizing that the solar system is roughly half as big, and then some dynamical event threw them out. And what we think happened is that this compact planetary system was surrounded by a disk of small bodies that had extended just outside the orbit of the ice giants to around 30 AU and contained basically 25, 30 Earth masses versus asteroids. And if you put that all on the computer and you integrate the orbits, you find that the system is not stable for long periods of time. And eventually what happens is that the orbits of the ice giants go unstable. They cross one another. They start gravitationally interacting with Jupiter and Saturn, which throws them out into this disk. The disk just goes kaplooey, not because of physical collisions, but because of the gravitational interaction with the planets. And that disk of material gets scattered all over the place. Most of it ends up in interstellar space, but some of it ends up trapped in the Trojans. And the gravitational interaction between the ice giants and that disk evolves them onto the orbits we see today. And actually, we can match the orbits of the giant planets in our numerical simulations.
One of the premises I didn't quite follow is that you said we know that Uranus and Neptune could not have formed much later than Jupiter and Saturn, and that was really one of the arguments that they must have formed closer in initially. How do we know that they wouldn't have formed much later on?
Well, it's a theoretical understanding. Once you get a planet forming and it's slowly accreting these small bodies, once we get to the point where the escape velocity from the planet is about the same as the planet's orbital velocity around the sun, the planets will scatter objects around rather than eating them. And so eventually what happens is they'll hand them off to Jupiter and Saturn if they're there, and Jupiter and Saturn will just knock them out of the solar system. So what we find is when you get to the point where the ice giants are a couple times the mass of the Earth, they will stop growing, and all their food will be fed down to Jupiter and Saturn.
So let's get back to the Trojans. Why do they, in particular, allow us to distinguish the various models of solar system evolution? And what does the NEAS model predict as far as they're concerned?
So one of the interesting aspects of Trojans when we started studying them from the ground is while we expected them to be a homogeneous population, basically all the same things that went into building the core of Jupiter, we see that they're very different from one another. In particular, the colors are very different, from things that are basically gray to things that are redder than Mars. And we think what that's saying is that represents material that comes from many different regions of the solar system, this disk that existed outside the orbits of the giant planets initially, and that the different colors are due to different formation temperatures because you're further from the sun. And so the NEAS model mixes all that up and delivers them to the Trojan swarms. And so by understanding, first of all, what those different colors mean, we don't have a good understanding of that. So looking at these things close up will help us understand that. We might be able to figure out where in the disk they formed, and then looking at the distribution of objects in the Trojans will allow us to understand how the planets moved around. That's the basic idea. Another thing that the NEAS model predicts is, I said that most of this disk goes away, scattered into interstellar space, but some of it not only ends up in the Trojan swarms, but they end up in the Kuiper belt and are the sources of comets that we see today. So the NEAS model basically predicts that Trojan should be the same as comets. And we've sent spacecraft to visit comets before, so we have a decent understanding of what they are. So one of the things we're going to test is how different the Trojans are from the comets.
And does the model also predict that these small objects would be sampled from a whole lot of different distances, and therefore you'd expect them to be very diverse rather than just homogeneous?
That's right, and that diversity is the key. That's what Lucy is designed to do. As I said, we see this diversity from the ground, and understanding what that diversity means will help us constrain how the planets moved around. That's the basic story. Lucy is going to visit more objects in orbit around the sun than any other spacecraft in history, because we need to get to a lot of them. In all, we're going to be studying 8 Trojans, 5 Trojan systems. 2 of our objects are known to have satellites. We discovered the satellites as we were studying these things and preparing for the mission. One of these objects, which is, I must admit, my favorite, you're not supposed to love one of your children better than the others, but this one I actually do, is an object called Patroclus, which is a near equal mass binary. It's a system that contains 2 objects that are almost exactly the same size, about 100 kilometers in diameter, in a circular orbit around one another. And I think that itself is an important clue to how the solar system formed and evolved.
Well, that's fascinating. One of the things about the Lucy mission also is that it's a so-called exploration mission that has gone to places that we've never been before.
Yeah, Lucy is going to this population. We've never seen them before. We basically have sent spacecraft to all the other small body reservoirs in the solar system, the main asteroid belt, the Kuiper belt, comets, but not Trojans. So I'm a theorist, right? So you start talking to me about Lucy, and I'm going to be concentrating on what it's going to tell us about the history of the solar system. But in a way, more importantly, we're going to a population we've never seen. And it's really the last small body population that we have to study. And what's more, while other small body reservoirs are contributing meteorites to the Earth, because of the Trojans' proximity to Jupiter, meteorites can't get to us from there. So these objects are really, really a mystery.
Let's talk about what the spacecraft looks like and what instruments it carries.
Sure. Because Lucy's job is to study the diversity, we have to be moving really quickly to get from object to object to object. So we're traveling really fast. Our encounter velocities with our Trojans range between roughly 6 and 9 kilometers a second. As a result, we're not stopping. We're not orbiting. We're not scratching and sniffing. Everything that we're doing is remote sensing. But yet we're trying to do everything we possibly can with those remote sensing instruments. So in particular, we have panchromatic cameras, which are going to be able to allow us to study at high resolution the geology on the surface of these bodies, counting craters, looking for maybe vents, because we think these things are related to comets. Maybe we'll see evidence that they were at one time active. We have a near-infrared spectrograph, which is going to be studying the chemistry of these objects. We have a far thermal infrared spectrometer, which is going to tell us something about how fluffy the surfaces are. And as we fly by these objects, we're going to be able to measure the Doppler shift due to the gravity. And so we're going to be able to get their mass. And because we're going to know their shape after the encounter, we're going to get an idea of what their internal density is, which is going to tell us something about their internal structure. The interesting thing about the Trojans is that we have a few densities for these objects, and the densities are always less than 1. So think about it. These objects are made out of rock and ice. We believe they're about half rock and half ice, and yet their density is less than ice, which means there are a lot of void spaces inside of it. And so we're going to be able to understand that as well. And of course, that tells us something about how they accreted, right? How fast they came together. Because if their density is low, whatever process formed them, when these objects came together to form them, they had to be going at really low velocities or they would become more compact. So understanding their density is critical to understanding their history.
You're going to be flying by at these very rapid speeds, as you said. So how long will you actually have upon approach and then as you leave to capture all your data?
So one of the interesting things about Lucy, and one of the challenging things about Lucy, is that it's a 12-year mission. But all our important science is going to be collected within about 24 hours. 2 hours on either side of close approach is where we're getting all our high-quality scientific data. So, first of all, we can't blink. Something can't go wrong, because once an encounter's done, we can never go back. We can't do a do-over. So we have to plan every second of what the spacecraft is going to be doing during these encounters. Also, we're not talking to the spacecraft during the encounter. After all, the light travel time is long enough that we couldn't say, no, do this instead. So it's totally autonomous, and everything needs to be planned beforehand. So although we launched in 2021, you might think we've had a long time to wait and we're sitting and twiddling our thumbs. But we have been very, very busy planning each encounter in order to make sure that we're getting the best science that we can.
So how close will you get and what kind of surface resolution will you get with your instruments?
So we're flying at a distance of a few hundred kilometers, 500-600 kilometers. And with the high-resolution spectrograph that we have, we'll get about 15 meters per pixel on the camera.
You mentioned that you're going to be flying by and going very fast and that you launched in 2021. So where has Lucy been traveling all that time and what trajectory is it taking to get to the Trojans?
So Lucy's trajectory is really spectacular. It's one of my favorite aspects of the mission. To be able to get to these objects, and they're very special objects. I said we're going by 5 Trojan systems to study the diversity, but we've been lucky that the objects we've been able to get to are interesting as individuals. Several of them would be worth actually sending a spacecraft to if that's the only place the spacecraft could get to. What I like to say is I'm a dynamicist. I study how things orbit the sun. So I've been worshiping at the feet of the celestial mechanics gods for 40 years, and they're paying us back. It's really, really a spectacular mission due to this really unique trajectory. But one of the things that we're doing in order to save money is Lucy launched on a very small rocket. Atlas 401. And as a result, when it first left the vicinity of the Earth, its velocity with respect to the Earth was really small. So we could use a small rocket. And what we've been doing is using a series of Earth gravity assists, where we fly by the Earth and use the Earth's gravity to slingshot Lucy out, to slowly pump up the orbit of Lucy so it can cross the orbit of Jupiter. And so that's taken some time. And so that's what Lucy's been doing basically. But on 2 of those orbits, we actually went through the main asteroid belt. Although we didn't get quite far enough to get to the Trojans, we did get to the point where we could get into the asteroid belt. And we did 2 flybys as tests of our system, right? Again, there's no going back. So testing the system and making sure we understand how to fly it was key. And so we've studied 2 asteroids so far, and they've turned out to be particularly interesting. One in particular is really interesting.
Tell us about the asteroids you encountered then.
Let me take a step back and point out that most asteroids that we know about are not named. All the objects that we're studying with Lucy, only 2 of them had names before we started. So we got to name a lot of these objects. For the main asteroid belt objects, we flew by an object that we named Dinkinesh, which is the Ethiopian name for the Lucy fossil. So let me take a second to talk about how we came up with the name Lucy. Lucy, the mission, is named after Lucy the fossil because we're arguing that these objects are the fossils of planet formation. And just like our ancestral fossils will tell us about our history, these objects are going to tell us about the history of the solar system. So we named the Lucy mission after the Lucy fossil. I should also point out the Lucy fossil was named after Lucy in the Sky with Diamonds. So if you actually look at our logo, we made sort of a connection to that our logo is diamond-shaped. So the first asteroid we encountered en route, we named Dinkinesh, which is the Ethiopian name of the Lucy fossil. Lucy was discovered in Ethiopia, and it currently is in their museums. Dinkinesh turned out to be one of the most fascinating objects I think I've ever seen. Because remember I said at the beginning, these things are interesting because they've basically remained unchanged over the history of the solar system. And that you need to have big objects in order to make geology happen. Turns out that's not right. If you have very small objects that are about 1 kilometer in diameter, radiation forces can actually change the spin rate of these objects over time. And as a result, they can spin up, and then centrifugal forces start putting stresses on the bodies, and they can crack, and pieces can fall off and form satellites. And all that can happen on really fast timescales, 10 million years or so. And that's what's happening on Dinkinesh. Dinkinesh is only 700 meters in diameter. And as a result, it's been spinning up and slowing down, and we see evidence of a big crack that's opened up in it. And it has this satellite that we named Salam, which is named after another fossil. And it is a contact binary of 2 objects that are roughly the same shape, that are stuck together. And all these things are probably very young and formed because of this radiation forces. So at a size scale of about 1 kilometer, really, really cool things can happen. And I didn't quite really appreciate that before we saw this object. The second object we went to, we named Donaldjohanson after the discoverer of the Lucy fossil. Actually, one of the cool things is that he was able to come to the encounter. So I think this is the first time that a person for whom an asteroid was named after actually was there to see it when this dot of light in the sky became a world. So that was pretty cool. Donaldjohanson is shaped like a bowling ball. Turns out that that's pretty common. So it didn't really hold any surprises when it came to its global structure. But it has some weird things going on on the neck between the two components. There seems to be some geology going on that we don't quite understand. So that's been interesting too.
Let's look forward then to your encounter with the first set of Trojans that you're going to. And you mentioned that the gods of celestial mechanics are rewarding you. And is that because basically you have a limited supply of fuel on board, so you can't really change course once you're speeding along all that much? So they have to be kind of lined up pretty much in a straight line for you to go from one to the other. Did that actually leave you with a choice as to which asteroids to visit? And if so, how did you actually make that choice?
Yeah, our first goal when we put together the mission was to try to run an experiment with as much control as possible. I told you that Trojans have very different colors from one another. So we tried to find two objects that are the same size and on the same orbit. So they've had the same basic history, but yet have very different colors. We did that so that we could say anything that we saw in differences between these two objects are due to their different compositions and not due to, say, the different histories. And we put together a list of about a half a dozen, that's all we could find, candidate objects, and then asked the people that designed the mission to see which ones we can actually get to within a reasonable amount of time and a reasonable amount of fuel. And it turns out there was one pair, okay? And that is the center of our mission, which is going to an object called Euripides, which is a gray-type asteroid, which is the first one we encounter in 2027, and then Oris, which is a very red object that we encounter in 2029. And that's when we're going through the first loop, going through the leading swarms of Trojans, the ones that lead Jupiter. So that's how we started. Everything else was just luck. And you might think it didn't require much luck. But one of the things NASA cares about when you put in a proposal to fly a mission through them is you need to make an argument of why you want to do it now. Why not wait to do the mission? Because after all, technology gets better as time goes on. And if you waited a decade, maybe you would get more science out of it. So we ran the experiment asking ourselves, what would happen if we were launching in 2030 instead of 2021, and tried to put together a list of targets. And we didn't find anything anywhere near as interesting. And again, we were really lucky. We maybe got 3 objects or 4 objects rather than the 8 that we're going to. And they were just uninteresting objects compared to the ones we're actually visiting.
Well, that's really very fortuitous indeed then, now that we know how unlikely this alignment is. So how long will it take to fly by all these systems in the first set of Trojans? And then what does the path of Lucy look like after you're done with those?
Okay, so as I said, we rattled around the inner part of the solar system for a while using Earth gravity assist to pump up the orbit of Lucy. Right now, it's in an orbit with a perihelion, a close approach distance to the sun, just inside the orbit of the Earth, and an aphelion distance, the furthest distance it gets from the sun, just outside the orbit of Jupiter. And that's where it'll be for most of its life. We're doing 2 orbits. The first orbit will take us into the leading swarm, and the second orbit will take us into the trailing swarm. And in the leading swarm, we're having 4 encounters in 15 months. So it's going to be very fast, but we're going to be very busy. Matter of fact, I'm worried about it. Then we come back into the inner part of the solar system, have another Earth gravity assist, which is going to allow us to target our final Trojan, which, like I said, this is my favorite, the system of Patroclus. We're only going to 1 object in the trailing swarm. And that's because we made the decision to go to a very low density region of the Trojan swarms in order to get to Patroclus. We could have flown through the center of the swarm and probably gotten a few more objects, but Patroclus is so cool that I decided that we needed to go after it rather than more targets. And so that's what we're going to do.
And the fact that it's an equal mass binary, does that make you think that it's more likely to be like a really pristine fossil, as it were?
Yes. So let's talk about this object and objects like it. When we look around the solar system, the inner part, let's call it the inner part of the solar system. And by inner part, I'm talking inside the orbit of Neptune. So in the region where planets actually formed, seeing two objects like this, these near equal mass binaries, are incredibly rare. I think we know of 3 or 4 of them. But if you look out in the region of the Kuiper Belt, the region beyond the orbit of Neptune, there's a place that we call the cold classical Kuiper Belt. And it is a place where we see asteroid-type objects that we believe to be pristine because they were far enough from Neptune that they weren't affected by the planet formation process themselves. When you look into that area, it turns out they're all near equal mass binaries, almost at 100%. So I think what that's telling us is that the first macroscopic objects to form in the solar system were formed as binaries. And indeed, modern theories of planet formation and planetesimal formation actually can explain that. And the idea is that the first macroscopic objects form because small things, things the size of a meter or the size of your fist, were concentrated due to their interaction with gas. And when they got concentrated enough, sort of like, think of them as like little star clusters, they became gravitationally bound to one another and then collapsed to form the big objects. By the way, they collapsed very slowly, which is probably why these objects have very low density. But when you model this, you find out is what's happening is that these clumps actually have a little bit of rotation. And as they collapse, angular momentum has to be conserved. So they spin up faster and faster and faster, like a dancer bringing in their arms. Angular momentum is conserved, so they need to spin faster as their arms move in. There's so much angular momentum in these systems that you can't fit all of it into one object. It would fly apart. So what nature naturally does, it turns out, is it makes two objects the same mass, but in orbit around one another. And that's exactly what we see in the cold classical Kuiper Belt. So we really think that these are the first real big objects. And if that's true, then Patroclus is one of those rare survivors that survived the planet formation process, which is very violent after all. Things are hitting each other, things are gravitationally flying by one another, which could rip these binaries apart gravitationally. That's why they didn't survive. But Patroclus did. So it's going to be really cool to look at that.
So after you finished with the second Trojan encounter with Patroclus, what's going to happen to Lucy? Where will its orbit take it?
It's going to be in the orbit that it's on basically now. That takes it out to Jupiter's orbit and brings it into Earth's orbit. We think there should be fuel enough, and if the spacecraft is healthy, I'm sure NASA will find a use for the spacecraft and do something cool with it. One of the interesting aspects of the orbit that it's on is it turns out it's very long-lived. It'll last in this orbit, if no one does anything with it, for about, on average, 2 million years. So we did something I think that was interesting. For those of you who know about the history of NASA, particularly early on, had this idea of sending messages to aliens, right? So the first spacecraft to leave the solar system, which were the Pioneers and the Voyagers, all have messages to the aliens. The Pioneers have these famous plaques. The Voyagers have record players, the sounds of the Earth. All that is focused on aliens because they're leaving the solar system. Lucy, on the other hand, is going to be in orbit in the solar system, and it'll last for a very long time. So we had an idea to put a plaque on Lucy, not with messages to aliens, but to messages to our descendants. You could easily imagine 100 years from now, maybe it won't be so interesting then, but 1,000 years from now, 10,000 years from now, hundreds of thousands of years from now, our descendants want to learn about us by going around the solar system and picking up our space junk. So we left them a little message. So take a look. It's online. You can see a picture of our plaque.
I know this is probably a bad time to ask you this, but once you have the data from a successful Lucy mission in hand, what would be your next preferred destination for a new space mission to help resolve further questions about solar system evolution?
Well, there are two places that I think I would like to go. The first is send another spacecraft out to the Kuiper Belt and study the cold classical Kuiper Belt. As I said earlier, there are regions of the Kuiper Belt that we think should contain the same stuff as the Trojans. And so being able to compare a 100-kilometer size thing in the Trojan swarms to something in the Kuiper Belt would be, I think, really interesting. But there's another place that we could go that's much closer. There's a population of asteroids just outside the main asteroid belt called Hildas. If the Nice model is correct, they were also captured at the same time the Trojans were. So one of the really interesting places to go is to a Hilda. And indeed, we've recently discovered that we can get Lucy to a Hilda at the end of its main mission. So maybe, if NASA decides to extend the mission, we'll be able to go to one of those objects too. Because comparing populations to one another, looking at diversity, like I said, is the key to figuring all this out.
Hal Levison, thank you very much.
My pleasure. It's fun.
To see pictures and illustrations that support this podcast, go to geologybites.com, where you'll also find a subject matter index of all the episodes. There you can also give me feedback, which I welcome, as well as sign up to get my emails about new episodes.